In this question, you will explore the concentration of a drug in the body when the drug is given repeatedly. Once a drug enters the body, it is absorbed into the blood. As the body breaks down the drug over time, the concentration of the drug decreases. Let C of T, measured in milligrams per milliliter, be the concentration of the drug T hours after the drug is given to the patient. The rate at which the drug is broken down is modeled as directly proportional to its concentration, leading to the next differential equation. dC over dt is equal to negative Kc. The initial concentration is D, where D is greater than 0. So when T is 0, C is D. And question A. By solving the differential equation, shows that C is D multiplied by E to negative Kt. So we need just solve this differential equation, and just by separating variables we get that dC over C is equal to negative K dt. Then integral dC over C, it's just formula from a data booklet. It's ln. In general it's over the absolute value, but since concentration is always positive, so we can write directly that it's ln of just C, and is equal to K is constant, and integral of 1 dt just T plus some constant of integration. Let it be, for example, A. Then how to undo this log? And ln is log to the base e, and you remember that log, for example, 2 8 is 3. Why? Because 2 cubed is 8. And it means that e to the power of this is equal to c. So c is e to negative kt plus a, and it looks like 2 to the power of 3 plus 5 is what? 2 to the power of 3 multiplied by 2 to the power of 5. So we can rewrite it as e to negative kt multiplied by e to the power of a. E, it's just a constant, a number, it's 2.7 and something, so it's a constant to the power of a constant, so it's just another constant, and let it be, for example, b. And to find this constant, we use the initial condition that when t is 0, c is d, and substituting it, we get that d is b e to negative k times 0, which is 0, so it's just b. So b is d. Hence, we get that c is d e to negative kt as required. The next, for the remainder of this question, we should use that k is 0.2. And question B, find the time in hours for this drug to reach 5% of its initial concentration. So we should find T when concentration is 0.05 of D, just substituting for C, and it's D e to K is 0.2 T, and we need just solve for T. You can see that D cancels. And you may use a calculator, plot two graphs, find the point of intersection of plot one graph e to this power minus 0.05 and find just x-intercept or 0. I apply ln to get ln of 0.05 is equal to ln of this e, but it becomes negative 0.2 t ln of v, which is 1. I just use that ln a to the power of b, it's just b ln a. In general, it may be ln log to any base. And then t is ln of 0.05 divided by negative 0.2. ln is negative, so minuses cancel. And ln of 0.05 is this, divided by 0.2, it becomes 15.0 to 3 significant figures hours. The next, the drug is to be given every t, capital T hours, and in constant doses. such that the concentration of the drug is increased by an amount d. Then question C shows that the concentration of the drug is d1 plus e to negative 0.2 capital T plus e to negative 0.4 T immediately after the third dose is given, 4 marks. So at time which is 3 times capital T, the third dose, let it be C3, it's directly D, and the second dose C2, it's D but multiply it by e to negative 0.2 T. Why? Because the first dose it's D, and after capital T time interval, which is equal to capital T, it is taken the second dose, which is also D, but from the first to the second dose time interval is what, capital T, and dose decreases according to this formula. So the first dose remaining at this moment of time, it's e to negative 0.2 T, and the third dose, it's D, and the second dose at this moment of time, it's e to negative 0.2 T, but the first dose at this moment of time, it's e to negative 0.2 times 2T, because 2 time intervals elapsed. And the first dose C1 is D, e to negative 0.2 times 2T. Hence, concentration remaining or total, it's the sum, and it's just D plus DE to negative 0.2 T plus DE to negative 0.4 T, and just factor out D to get the required result. The next, immediately after the nth dose is given, the concentration of the drug is D1 plus E negative 2T plus E negative 4T plus so on up to E to negative 0.2 and minus 1 T. And question D shows that this concentration can be expressed as D multiplied by one minus E negative 0.2 and capital T 1 minus E to negative 0.2 T. For this, you can see that, for example, when n is 3, we get the previous, so we get 1 plus e to negative 0.2 T plus e to negative 0.4 T. And definitely it's a geometric sequence, and we need just find the sum of geometric sequence, and you can see that the first term is, if we consider only this without d, so u1 is 1, and common ratio, definitely you can see the second divided by the first, its ratio, common ratio is e to negative 0.2 T, and you can check that it's always the same, the third divided by the second, it's also this value. And the question is, because formula is the sum is the first n terms is what u1 1 minus ratio to the power of n and 1 minus but the question is how many terms are there, n or n minus 1 or n plus 1. And let's check when n is 3, 1, 2, 3, you can see that when n is 3 we get this, so it from 1 to this there are n terms. For example, let's check when n is 3, you get 1 plus this up to this 1, 2, 3, 3 terms. So there are n terms in total, and it becomes u1 1 and 1, or let rewrite directly that you rewrite this and continue that it is equal to d, and for this expression we apply this formula, sum of the first n terms, so substituting n for n into the formula, it becomes u1, it's 1 multiplied by 1 minus ratio e to negative 0.2t to the power of n, and divided by 1 minus ratio e to negative 0.2t, and it's like 2 to the power 3 and 2, 5, it's just 2, 3 times 5, so it just becomes d 1 minus e to negative 0.2 nt divided by 1 minus e to negative 0.2 t as required. The next, after patient has been taking this drug for a long time, it is required to keep the concentration within a particular range so that it is both safe and effective. Let Hn be the highest concentration of the drug in the body for the interval t is greater or equal than n minus 1, t and less or equal than nt, and Ln be the lowest concentration of the drug in the body for the interval, same interval. This is shown in the following graph. H infinity is defined as limit when n tends to infinity. It just means that many doses are taken or over a long period of time. H n and L infinity is defined as limit n tends to infinity Ln. And question E. Find in terms of d and capital T an expression for H infinity and L infinity. 2 marks and 3 marks. And we use the previous result. This and since it is given directly, so we consider limit n tends to infinity and What about hn? Hn, it's when, it's just when some n's dose is taken, but L is the lowest possible dose. It's just before the next dose is taken, and since it will be equal to this h multiplied by e to negative 0.2 t. So h infinity, it's limit when n tends to infinity, and just after n's dose is taken, and the remaining or total concentration is given by this. So we just consider this. It's d 1 minus e to negative 0.2 n capital T divided by 1 minus e to negative 0.2 t, and it is equal to, notice that n tends to plus infinity, not capital T, and e it's 2.7 and something, and negative t is positive, n is also positive and very large, so 2.7 to negative and very large number is the same as 1 over 2.7 to very large positive power, so it becomes 1 over number which is greater than 1 to very large power. It's 1 divided by very large number, and 1 divided by very large number, no, it's it tends to 0, it's just 0. So this tends to 0, and it becomes d 1 minus 0 and divided by this. I repeat that n is very large positive, not t. And L infinity, it's the maximum, or it's the lowest possible dose after a long period of time. It's directly from the graph, it's just before the next dose is given, and it is given that its limit n tends to infinity, but since we consider just before this moment of time, for h we consider this moment of time when n's dose is just given, but to get the lowest value, it's just before the next is given, but it means that time interval capital T elapsed from the n's dose is given, so remaining amount becomes this when just the n's dose is given, but it is multiplied by e to negative 0.2 t. And this tends to 0 when n tends to infinity, so it becomes d e to negative 0.2 t divided by 1 minus e to negative 0.2 t. Then F shows that h infinity minus L infinity is d. 2 marks. So just consider h infinity is d over 1 minus e to negative 0.2 t minus L infinity, it's d e to negative 0.2 t 1 minus, and we can rewrite with common denominator, and we can factor out d. Here it becomes 1 minus e, and you can see that it cancels, so we get d as required. The next shows that 5 ln of h infinity over L infinity is capital T. So let's consider 5 ln of h infinity. It's d over 1 minus e to negative 0.2 t divided by L infinity. It's d e to negative 0.2 t and divided by, so it becomes the numerator 1 minus e to negative 0.2 t. Just division of fractions. And you can see d cancels, this cancels, so we get that it is equal to 5 ln of what? 1 over e to negative 0.2 t, and it's 5 ln of e to the power of 0.2 t. It's 1 to 5 to negative 3, the same as 5 to power 3. And log ABC is equal to C log AB. So it's just 5 times 0.2 t ln of E, but ln of E is just 1. So it is equal to what? 1 t, or just t as required. The next, it is known that this drug is ineffective if the long-term concentration is less than 0.06 and safe if it is never exceeds 0.28. Question G. Hence, for this drug, find a suitable value for D, 1 mark, and capital T, 1 mark. So notice that there are only 1 and 1 marks, so it must be something very easy, and definitely it's not required to consider some inequalities, and it is given that to be effective, it must be, concentration must be greater than 0.06 total or remaining, and to be safe, it must be less or equal than 0.28. But again, since it's 1 and 1 marks, we can see that lowest it just this 0.06, and highest it just this 0.88, and it is suggested that the suitable values for D and T can be found just directly from the previous answer. So H infinity minus L infinity, so maximum minus minimum, it's 0.22, it's a suitable value for D. And from this, that 5 ln of highest 0.28 divided by 0.06 is equal to T, and we can calculate it using a calculator. So 5 multiplied by ln of 28 over 6, and it's 7.70 hours. And it's milligrams per milliliter. Or you may consider just expressions for L and H and just take these critical values to be equal. So H to be equal to this, and L infinity to be equal to this, and solve for capital T and D, but it's not required because we can use, or it is suggested that you use the previous result, and it's because it is given only 1 and 1 marks. The next question H. For the value of D and capital T found in part G, find the proportion of time for which the concentration of drug is at least 0.06 milligrams per milliliter between the first and second doses, 2 marks. So we remember equations that concentration is what dE to negative 0.2 T, and for this D it's 0.22 and multiplied by e to negative 0.2 T, and we need it should be greater than 0.06, so we can consider just that it equals and just solve for T. Solve for T. And it becomes dividing by 0.22, so it becomes 6 over 22 or 3 over 11, and then ln, or actually you may plot 2 graphs or 1 graph and just solve using a calculator, and it becomes ln of e to this negative 0.2 T, and again it's negative 0.2 T ln of e, which is 1, and hence T is ln of 6 over 22, and it's negative, so minus is cancelled, and then divided by 0.2 to get 6.50 to 3 significant figures, but it's intermediate result, so let's take it to be exact, 4964 and so on hours. And definitely it's a decreasing function, so concentration decreases from D to up to the minimum value, which is 0.06 for this time interval. And question is, I repeat, for the values of D and capital T found, find the proportion of time for which the concentration of a drug is at least, it means greater, but since function is decreasing from t0 up to this moment of time, so during this time interval, and we need out of capital T this 7.70, and it becomes the required proportion of time, so that dose is greater than 0.06. and actually it would be better to take T also be as exact. And it's 70 just to 2. And divided by 7.70, and it's approximately 84.3% of time. To 3 significant figures, and you may add here multiplied by 100% to get to be as percent. And the last question: suggest a reason why the instructions on the label of the drug might use a different value of capital T to that found in part GII 1 mark, this 7.7 hours, and again it's only 1 mark, and any reasonable answer that engages with the model in a practice sense. So for example, rounding to 8 hours leads to 3 times a day. It means just easy to schedule. Or 7.7 hours is difficult to schedule. Or avoiding giving too much of the drug. And given the patient an overdose. And that's all for this question.